Hi, my name is Dr. Deshawn. In this video, we're going to find derivatives implicitly. Before we do our implicit derivative examples, let's take a look at this review problem over here on the board. We want to find the derivative of this review, and this is y equals x to the fifth minus 3x to the fourth. If you were to graph this, this is a function. This curve right here is a function. So we want to find the rate of change. Derivative represents a rate of change at any point on the function. This function has infinitely many points. We want to find its rate of change, and we certainly can find rate of change at all the infinitely many points on this function. How would we do that? Well, to find our derivative, let's use the notation dy dx, dy over dx, the derivative of y with respect to x, and we'll just go ahead and use our power rule on this example. So you bring the 5 around front, so you have 5x to the subtract 1 from the exponent, okay? Minus, then bring the 4 around front, 3's there, so multiply, so you have 12x to the third power when you subtract 1 from that exponent. So here is the derivative, how to find the rate of change of all the infinitely many points on this function. So we want to learn implicit differentiation, and where do we ever use implicit differentiation? Okay, well, everything we've been working with up to this point has been a function, has been f of x equals, g of x equals, h of x equals, y equals. And so when it's a function, explicitly we'll just go and use the power rule, the chain rule, the quotient rule. We'll use our rules to find the derivatives, okay? With implicit differentiation, this applies to curves that are not functions. What if you have a curve that's not a function, that you cannot write in y in terms of x explicitly? You can't write this. We have y to the third power in this example plus y squared minus 5y minus x squared equals negative 4. Here's our example we're going to do first. Now, there's no way to get y equals, okay? So we can't get y equals. What does that mean? That means that this curve right here is not a function. What does this curve look like? Well, if you wanted to see a graph of what this curve looks like, this is the idea. This is what this curve looks like. And you can see this is not a function. But just because it's not a function, can we still find the derivative? Can we still get a rate of change at each of these infinitely many points? Sure we could. We just have to do this implicitly instead of explicitly. So this is where implicit differentiation comes in. So what you do first with these curves, you're going to go to every single term, and we want to differentiate every single term with respect to x. With respect to x, okay? So here we go. So the first variable here, we have y to the third power. When you take this derivative, you're going to have 3y to the second power when you differentiate, and we are differentiating that as the derivative of y with respect to x. You need to write dy over dx after it because we differentiated this as y in terms of x, okay? The derivative of the next term, the derivative of y squared, is 2y, and that is the derivative of y with respect to x, followed up with a dy dx, okay? Minus the derivative of a minus 5y is negative 5, and that's the derivative of y with respect to x. Okay, the next term, the derivative of x squared, okay, well that would be 2x. Now be careful here, this is the derivative of x with respect to x, okay? We're differentiating every single term with respect to x, and then the derivative of a constant is just 0, so we don't have to write anything with that, okay? So you differentiate every single term with respect to x. We differentiated the y's with respect to x, followed these up with a dy dx. We differentiate the x with respect to x. Now, what about differentiating the x with respect to x? When we differentiate the x with respect to x here, the dx over dx, this is just 1. We really don't need to write that down. All right, so in other words, when you differentiate a term that with an x alone, with an x in it, well, then you just differentiate the x because you differentiate with respect to x. But when you differentiate a y term, you've got to follow that up with dy dx expression, okay? So let me write this again without the dx over dx in it. So what do we have here? We have 3y squared, and that's the derivative of y with respect to x, okay? Plus 2y, and that's dy over dx. All right, minus 5, that's dy over dx, okay? But then minus 2x, just the minus 2x, because when you differentiate with respect to x, just leave it alone. We're differentiating with respect to x, okay? When you differentiate a y term, followed up with dy dx, okay? We want to solve for dy dx, so what we need to do next, algebraic thinking here, we're going to take the dy dx terms and move them to the left side of the equation. Let's take the non-dy dx term, move it to the right side. So you have 3y squared dy over dx plus 2y dy dx, okay, minus 5 dy dx, and then move the 2x to the other side. Okay, so we're here, all right? And then we want to solve for dy dx, so factor out the dy dx. Let's factor out dy dx from the left-hand side, factor it out. 3 terms with the dy dx, so factor it out. Take it out of this term, we've got 3y squared, okay? Take it out of this term, we have 2y left over. Take it from this term, a minus 5. All right, the right-hand side is the 2x, all right? And we want to solve for dy dx. We want dy dx by itself because that's what the derivative of the function representation is. So what is dy dx? Well, to get dy dx, we're going to divide both sides by this quantity. So you're going to have your final answer of 2x over, and then we have what here? 3y squared plus 2y, and then minus 5. Here is your implicit derivative for this curve up here, okay? So this is the strategy we use to find derivatives when your curves are not functions. When they're not functions, when we can't do explicit y in terms of x, we have to go ahead and differentiate implicitly this way. Every term you still differentiate with respect to x, but you have to handle it this way when your curve is not a function. All right, so let's do another example. Let's do another example that has a little bit more rules in it. We're going to do another, and then we'll do a trig example after that. So let's do another example right here in this space on the board. So let me erase this one, okay, so we can get example number 2 up here, all right? So we'll erase this example right here. We'll do example number 2. Now, example number 2, it's a curve. It's got a name. It's a curve with a special name to it. All right, so in case you wanted to look it up. But example number 2 is going to look like this. Okay, so example number 2, we've got y squared times the quantity of x squared plus y squared. Okay, and we're going to set that equal to 2x squared. So here's example number 2. Okay, so this is the curve. We're going to go ahead and implicitly find the derivative. You can see that we're not going to just try to get a y equals for this. Okay, so we're going to find the derivative here. This is not a function. So, but this curve right here, I told you, it has a special name. This is actually called the Kappa curve. In case you wanted to look that up, that's called the Kappa curve. All right, and so we are going to go ahead and we're going to find the derivative of this implicitly. And so in case you wanted to look it up, or here's what the Kappa curve looks like, okay? So we're going to go ahead and take this curve right here. This is the Kappa curve, and we're going to go ahead and implicitly differentiate this Kappa curve. All right, so I would start this problem here by maybe simplify a little bit, simplify the calculus if we maybe go ahead and take the y squared and distribute it. So let's take the y squared and distribute it. Y squared times x squared, it's that first term will give me the x squared times y squared. And then when I distribute it to this term, y squared times y squared, so I'm going to keep that base and add those exponents, right? Equals 2x squared on this side. Okay, so I mean you could leave it like this, or this might be a little bit easier to differentiate. Okay, all right, and then when we go ahead and find this derivative, now here, this first term right here, we want to be careful, don't we? Okay, to differentiate this first term, we have to use the product rule. So remember the product rule from your calculus class. We got to use the product rule to differentiate this first term. So product rule, be careful, okay? So we're going to take what's in that first expression there, we're going to just bring it down, okay? Product rule is when you have two functions times. You bring the first one down, okay? You're going to multiply by the derivative of this y squared. We're differentiating with respect to x. So the derivative of y squared is going to be 2y, and that's the derivative of y with respect to x. Make sure when you differentiate a y, you follow it up with a dy dx, okay? Plus, then you take this second term here, the y squared, that gets brought down for the product. We'll bring it down, and you don't have a dy dx here because we didn't differentiate. We just bring it down. That gets multiplied by the first term. All right, the derivative of the first term. All right, so here is our product rule application for this. There's the derivative of that first term right there, x squared times y squared. So x squared times like your u times v. So product rule, if that's a u and that's a v, then it's u v prime, okay, plus a v u prime. Bring the first down, differentiate that second expression. So y squared, the derivative 2y dy dx, differentiate a y, followed up with dy dx. Plus the second, derivative of the first, okay? Now we're at this term. What's the derivative of y to the fourth? The derivative of y to the fourth is 4y to the third. We just differentiated a y. That's the derivative of y with respect to x. When you differentiate a y term, follow it up with dy dx, because we're differentiating every term with respect to x. That's a derivative of y with respect to x. And then on the right-hand side, what's the derivative of 2x squared? Bring the 2 around front. That's going to be 4x to the first power, 4x. And that's the derivative of x with respect to x. We don't have to write that, okay? So you differentiate with x, we just leave it alone. We're differentiating with respect to x. Derivative of a y, follow it up with dy dx, okay? What do we do next? Dy dx terms on the left, non-dy dx terms on the right. So here we have 2x squared y dy dx, okay, minus 4y cubed dy dx. We're going to keep the plus 4y cubed dy dx. The dy dx terms stay on the left, and these are already on the left, so you just bring them down, okay? The right-hand side, we're going to have 4x, and we're going to need to subtract this to move it to the right-hand side, minus 2x y squared. So we're here, okay? So dy dx terms on the left, non-dy dx on the right. Let's factor out the dy dx, okay? So now, sure, there's a few other terms that you have in common, but we want to solve for the derivative. Just factor out the dy dx, take the dy dx out of this term, 2x squared y, and then take the dy dx out of this term, 4y cubed. And the right side, you have 4x minus 2xy squared. All right, and then finally, solve for dy dx. So what is the derivative? Here's the derivative expression, dy dx. For this expression here, we're going to have 4x minus 2xy squared in the numerator, and then the denominator 2x squared y plus 4y cubed. Okay, so here is kind of busy, right? But this is what the derivative of our Kappa curve. This is the derivative of our Kappa curve. So implicit differentiation, when your curve is not a function. When your curve is not a function, then we need to implicitly find the derivatives so we can represent all the rates of change at all the infinitely many points on our curves that are not functions. So here's example number 2, differentiating the Kappa curve. All right. Okay, so let's do a trig example. I've got one more example for us to do. Let's do a trig example. So let me move this one out of the way. All right, and then let's do a trig example. Example number 3, and we'll do trig. Okay, so anytime you have a curve that's not written as a function, then you want to utilize your implicit differentiation here. Okay, so trig example: x times the cosine of y equals 1. This is our third example. This will be our last example. This is our trig example. Okay, so let's do a trig example. So now, what does this curve look like? All right, so x times the cosine y equals 1. Here's a graph of x times the cosine of y equals 1. Okay, so we have a curve that we want to find the implicit derivative. We want to implicitly find the derivative. Okay, so the steps. What do we do first? We're going to differentiate every single variable with respect to x. Derivative of an x, leave it alone. Differentiate a y term, follow it up with dy dx. Okay, then you're going to collect all your dy dx terms on the left. You put your non-dy dx terms on the right. All right, then on the left side, factor out the dy dx, okay, and then solve for dy dx, and that's your derivative. That's how you're going to find your derivative implicitly. Those are the steps, okay? So let's take a look here. All right, on that left side, we have x being multiplied by cosine y. So again, we have to utilize the product rule. We have to use the product rule on the left. We have an algebraic expression in terms of x times a trig expression in terms of y. So our product rule, remember the product, so if you have u times v, the product rule would be u v prime plus vu prime. Okay, so the product rule. So you take what's in that first box I have here, the x, you just bring the first down. Okay, that gets multiplied by the derivative. The derivative of cosine y is negative sine y, and then dy dx because you're differentiating, a y term. Okay, so now we're halfway through our product rule. We bring the first box down, the first expression comes down, x, Derivative of cosine y, negative sine y, dy dx. Anytime you differentiate a term with a y in it, you got to follow it up with dy dx. Plus, now we're going to bring that cosine y, just bring it down. Just bring it down. Okay, so we just bring that down. No dy dx here, we're just bringing it down times the derivative of the first term. Okay, so here's your product rule with the left side. The right-hand side, derivative of a constant. Okay, so that goes to 0. All right, now what? Dy dx terms stay on the left. So what do we have here? Negative x sine y dy dx. Dy dx term stays on the left. Non-dy dx moves to the right, so I'm going to subtract the cosine of y from both sides. So we're here, okay? And then solve for dy dx. All we have to do now is just divide both sides by negative x cosine y. So dy dx here, dy dx is going to equal, these negatives will cancel, so I'm just going to write cosine of y over x times the sine of y. And here is your derivative. Here is your implicit derivative for this curve here, x times the cosine y equals 1. All right. I suppose there's another way we could write this answer. You could, keep the x's in the denominator, right? So you could pull the x, so 1 over x, and then cosine of y over the sine of y. So the cosine y over sine y, that's cotangent. All right, so you can also represent it this way. All right, so implicit differentiation. So first of all, we use implicit differentiation when we want to find derivatives of curves that are not functions. Okay, so if they're not functions, then this method works beautifully when the curves are not functions. So how do we actually do the process of implicit differentiation? Just a few steps. Step 1, you want to take every single term and you want to differentiate with respect to x. Every term gets differentiated with respect to x. And then once you have that calculus part done, your algebra strategies, you're going to take all those dy dx terms to the left side, okay? Non-dy dx to the right. All right, and then you're going to factor out the dy dx, solve for dy dx, okay? So implicit differentiation, you differentiate every term with respect to x. Derivative of an x, leave it alone. Derivative of a y, you follow that up with dy dx, okay? And then solve for dy dx. And that's it. So there's implicit differentiation. If these videos help you at all, would you please subscribe if you would. There's a button down below, so just please consider subscribing. Thank you so much. Take care, everybody. Thank you. Bye-bye.